Video, we will discuss on the average and RMS value calculation of a half-wave rectifier and a simple problem on that. Here, if you look at a half-wave rectifier, in this half-wave rectifier, if you have only one diode as a switch, then it will only pass on the positive half cycles of the source voltage to the load, and then negative half cycles are going to be blocked. Now you can see, if you're getting this kind of response of the voltage and the current from half-wave rectifier, how do we get average value of the load voltage? And the current across the load is just going to be voltage upon the value of the resistance, as we are looking at a half-wave rectifier with just a resistive load. So we can see that the current will be differing in a magnitude but not in shape at all. We don't have inductor and capacitive filters being added in this particular circuit. Now, if you wanted to get the value of the average load voltage, average value of the voltage is average over the time period t, and that is nothing but 1 upon t, that is the time period, and area of that particular waveform is what is calculated through the integral. In this case, the total time period of this particular waveform is 2 pi, so the time period we substituted as 2 pi. But the average or area under the waveform, if you want, you do not have any waveform after pi till 2 pi, so we will consider average value only from 0 to pi here. So 0 to pi, my output voltage is following exactly the source voltage. So 0 to pi, I have to integrate Vm sine omega t, which is nothing but my source voltage itself. Now this is how we get average value of the output voltage. If you try to simplify that, Vm upon 2 pi, and sine omega t integration is minus cos omega t, whereas your limits of integration are 0 and pi. If you substitute that limits of integration 0 to pi, your average value of the output voltage turns out to be Vm by pi. So 1 upon pi is 0.318, and you can say that your output average voltage is 0.318 times of Vm. As we see that the value of the current is exactly in the same shape as the voltage, but the difference is voltage upon resistance is the value of the current for us. The average value of the load current can be simply expressed as voltage upon the resistance. So average value of the voltage upon the resistance, and we just express it as 0.318 Vm upon the value of the resistance itself. When it comes to the RMS value of the output voltage, it is root mean square. So we have square root, mean, and square of that is what we consider. So we have root and mean is 1 upon t, square of that voltage, VL of t. What is the load voltage here? So now when you find the mean, again the same as the previous case, 1 upon 2 pi, because the duration of that voltage is 2 pi. And when you want mean square, root mean square, mean is an integral, but in order to find the square of the voltage, we have the voltage exist only from 0 to pi, so we find mean square only from 0 to pi. So square of the voltage there. So the only difference that we have from the RMS to average here is the square root, and also we have the square of the voltage in our integral. Now if you try to simplify that, then you need to find an integration for sine omega t square, where we try to write sine omega t whole square as 1 minus cos 2 omega t by 2, and then simplify the integration. Then we'll be able to get the RMS value of the voltage as Vm by 2. Now this is 0.5 Vm. This is the RMS value of the load voltage. Similarly, if you wanted to get the RMS value of the load current, just the load current is voltage upon the resistance. So we can just calculate that RMS value of the load current as voltage upon the resistance, which is 0.5 Vm by R. This is how we get average value of the load voltage and current. RMS value of the load voltage and current can be simply calculated through the respective integrations and derivations. If you want to solve a problem on this half-wave rectifier, where in this half-wave rectifier we have only resistive load with a resistive impedance as 25 ohm, and it is supplied by an AC voltage source. Let's say that the secondary of that voltage itself is 110 volts with a frequency of 60 hertz. Then we need to calculate what is the average value of the load voltage and load current, and RMS value of the load voltage and load current. Now we've already seen that the value of output voltage V naught, RMS if you want, it is V max divided by pi. And if you want I naught RMS, this is, sorry, so we've already seen that the output voltage average value is V max upon pi, and output current average value is V naught average divided by the resistance value. And similarly, if you want an RMS value, V naught RMS is V max by 2, and I naught RMS is simply V naught RMS divided by R. Now V max is talking about the maximum value of your source voltage. Now if you wanted to get the maximum value of the source voltage, RMS value of the source voltage is given as 110 volt. So that is going to be root 2 times of 110 divided by pi. This is going to be root 2 times of 110 divided by pi multiplied by resistance value as 25 for us. Similarly, V max is root 2 times of 110 upon the value as 2. Now this is going to be root 2 times of 110 divided by 2 times of the value of the resistance is 25. This is where we'll be able to get the values of average voltage and current output and RMS value of voltage and currents. So you can see that the respective values of V average and the respective value of I average. And the RMS value of voltage and current can be calculated like this. And next, if you wanted to get the power is nothing but VRMS, IRMS. So power is that something that corresponds to the RMS value of the voltage and current. And now both are in phase, so we don't have any phase angle also here. So we can say that P naught is V RMS square by R. You can get that power as 241.98 watts.